start the recording. Hello, everyone. This is the Econometric Methods workshop number 9, and today we're looking at binary data. I shall switch screens as necessary, but we need to open Stata and open the data set. Okay, so let's do that. I shall switch off the camera and then switch on the sharing of the data set, so you will occasionally not see me, but that's not a bad thing, I guess. Here we go. So I'm going to share my screen. Okay, you should all now be able to see my status screen. Can you let me know if you can see that? Let me know if you can't see that. In the chat. So, can you all see Stata?
Yeah, we can see Stata.
You can. You're logged in and collaborate, yes?
Yeah.
Excellent. Right. That's a good idea. All right. So we've opened Stata. What we need to do now is open the data set. The data set is called SIG, and it should be on the website. What's on the screen here? That's no good. Need to have that. Okay, so I'm going to open the data set via my do file. As usual, I have slightly more things on the my do file than you might have. It's just for teaching purposes. Open SIG 2021. And then generate a, in Peter's code, which he hasn't posted up, he uses the variable male, and in my code, I use the variable gender. So if you want to follow my code exactly, you need to create a new variable gender, and that's G for generate, gender equals male. Okay, if you want to follow my code exactly, that's what you need to do. But if you want to follow Peter's code, and Peter's going to put up the do file a bit later, then he uses male in his code. All I've done is change that to gender. All right, everyone? Can they see that online? Yes? Can you all follow that online? Okay, so thank you, Mary. So let's have a look at this data then. It's useful when you load data to have a quick browse, and the best way of doing that is Codebook or Describe, or even use the browse facility up here, whichever you like. If we click on the magnifier in Stata, everybody should see the data here, or you can use Codebook and then either the name of the variable you want to look at or all the variables. Hit return to get all the variables, and then just quickly scan through them. So, for example, obs is the first variable. It goes from 1 to 1,000, and in units of 1. The next one is y, which is unlabeled. These variables are unlabeled, and you may want to label them a bit later. So is everybody okay with how to get up to having a look at the data? Quickly, just using Browse, Codebook, or whatever. Okay. And if you wanted specific details about specific variables, then you could try sum and then double click on the variables list, and it will give you a summary statistics. These are the minimal summary statistics, of course. The more detailed, if you typed sum, the name of the variable, comma, detail, you'd get much more details of summary statistics, things like the percentiles and so on. All right, everyone good with that? Let's go now to what we're supposed to be doing. And can everybody see the list of questions today? Can everybody online see that? Tell me if you can't. Maybe I have to change. Again, I'll stop sharing when I am sharing, and then maybe share all screen, which might help. I'll share my entire screen. You should be able to see everything then, as I switch backwards and forwards. Okay, so you should all be able to see the workshop questions now. So this file sig contains a sample of 1,000 individuals from a developing country, where Y indicates 1 if the individual smokes, or 0 otherwise. The age variable is in years. Income is in thousands of pounds per week. Male is 1, 0 if female. And I've just changed that to gender. So gender will be 1 if male and 0 if female. And there's a class variable as well, and it has 4 categories. 1 if the individual is professional, 2 if they work in intermediate services or the intermediate industry sector or whatever, 3 if they're manual workers, and 4 if they're unemployed. And you're asked to describe the 210th individual in the sample, and somebody can give me the details of that, please, in the chat. Can somebody tell me what the details of the 201st individual are? You guys know how to do that? Type list in 201. List in 201 should give you what you need. Age is 31, correct. Income is 0.555 or £555 per week, which is quite a high income. They are female, correct? Good. So we're all able to get up that information. So the code would be list in 201, and we get the table of output there. Hopefully you'll be able to see all of that. Yes, this is should be straightforward for you nowadays. Okay, they work in class 3, which is manual. Well done, thanks James. So find the mean of variable y, find the mean of the number of individuals that smoke, and what does this mean represent? Number of ways to do that, and the easiest is in the summary of y. So sum y will give you what you're after. So you could go sum y, or you could just type mean of y, and the code will give you this, the actual mean. And what does that tell us? What does the mean of y tell us?
Ratio of smokers?
The
Ratio of smokers?
The proportion of the observations that are reported as smoking. So just under 39% say they are smokers. Are we good, everyone? Okay then, so the next thing we must do is estimate a logit of the decision to smoke using age, age squared, income, and male as explanatory variables. And you can see the code there. You can either create age squared using the generate command, or you can use the factor notation. It's easiest to do the factor notation, but in my do file, I've done both. So if you wanted to do manually, you do gen age squared, and the code for that is age using the up arrow, or the up chevron, and 2. Age cubed will be up chevron 3, etc. Okay. And then when I create variables, I like to label them, and then you can run the logit with that. So this is the code if you were doing it without factor variables. This was what you'd have to use pre Stata 16, Stata 15, and so on. Didn't have factor variables, factor notation in it, so you'd have to do it manually. But here is the code in the question, and you will see that it's exactly the same as in the question. So I'll do that one.
Sorry, so why do you use QUI for the gen age squared?
Okay, that's just to not have Stata echo the output. So quietly, it stands for quietly, yeah. So if you look at the Stata output that I've done, it doesn't. There isn't much of an output to put here. But what would normally happen here, if you did it without quietly, you'd get something like so many observations created, and you could, in Stata, you can set that manually. You can set observation numbers and so on. So the output that would be created when you do generated is suppressed when you use quietly in front. You don't need it. It's just programming stuff, really. Okay, so what have we got? We've done this logistic regression with the age squared variable, or you've done it with the factor variables, and there's the output. And so what do we need to do then? We can make some statements. Notice that the process, as we talked about on Monday, is an iterative one, and these are the iterations. If you wanted to suppress these on your output, you just put, when you're looking at the logit, when you put the command in, the logit is the regression command. At the end, you'd put no log. If you wanted to suppress, and this is small here, there are 7 iterations before it reaches the maximum likelihood. But in some cases, it runs on and on and on. And so you may not want to have that. You just want it to work on its own and just give you the output, and the output will look like this. Okay? And so, what do we say? What can we say with this? So the parameter values here are the maximum likelihood estimates of the effects or the influence of these covariates on the probability of smoking. All right? And so the parameter values are the maximum likelihood estimates of the population statistics. And we interpret each of these in the usual way. We say that for a unit change in age, we would expect the probability of smoking to increase. And if age squared, to decrease. Income to have a negative effect on the probability or the propensity to smoke. And gender suggests that males are more likely to smoke than females. Yes? Cons doesn't really have much of an interpretation here, but two ways of looking at it. It's what is the influence on smoking that is not captured in your model when those things are zero, okay? But it isn't really really helpful in logit analysis, in limited dependent variable models. Okay, so any questions so far? Any questions in? Sorry, just shut down Teams. I'm not quite sure why it's popping up all the time. I didn't get how you interpret age. Okay, let's go through the interpretations then. Someone's asking how to interpret age. So age, the coefficient on age, maximum likelihood coefficient on age, so that for a unit increase in age, if age is increasing 1 year, then that is the effect on the probability of smoking. So it's positively related to the propensity to smoke.
So do we interpret that to mean as for every year someone gets older, then 52.8% more likely to smoke?
No, it's not a percentage. It's a percentage points. So it's whatever this is measured in, and that's 1 or 0. So it's a percentage point interpretation. It's not a percentage, overall percentage. Okay.
So their propensity to smoke goes up by 0.528
percentage points for every extra year, every year older they are. Does that answer your question in the how do you know that males are more likely to smoke? Sorry, Mary, did that answer your question about age, first of all? James, I answered QUI before. QUI means quietly. Tell Stata to ignore the output from the command. Mary, did I answer your question about age?
Not really, Joe. Sorry.
Was that yes?
No.
Did you say yes?
No.
I didn't answer it. I thought I did. So the interpretation with respect to age is that for every additional year, the propensity to smoke is positively related to age, and it goes up by 0.53 percentage points. Okay? With respect to the other question, how do we know males are more likely to smoke? Because males, gender in my regression and males in the in the one that some of you might be doing, is only 1 or 0. And so to have any coefficient in gender refers to the male compared to the base category, the excluded category, which is 0. So this refers to males. If there's any coefficient here, it can only refer to males. And that you compare that to the category that's excluded, which is female. So males are more likely to smoke, predicted more likely to smoke than female with this data. Does that answer your question, Aaron? Okay, there is no interaction. I don't know how to pronounce your name. How does somebody pronounce this name? It's a Thai name, and I'm not going to attempt it to embarrass myself or somebody else. But you're asking about the interaction. There is no interaction yet because we haven't created an interaction term in this regression. This thing here, this is not an interaction as such. It's simply age squared. When you use factor notation, when you use one variable, one hash, it's saying square it. Okay? So this then implies that age does not have a linear effect on the propensity to smoke. It has an inverted linear effect. Sorry, an inverted U effect. All right? So we can say age has a non-linear effect on the propensity to smoke. Somebody's just put something in the chat. Let me get to that. Okay, thanks. Right, so let's move on. The next thing we're asked to do is to provide the average marginal effects of the three variables age, income, and male. And to do that, type margins, dx, age, income, and male. So this relates to the average marginal effect of each of these variables. Okay? So let's do that. Get back to Stata, my do file. Let me see that I did the first one anyway. Yeah. So quickly do that, and you should get this. My code simply asks that I show coef legend post is just asking Stata to tell me what the coefficients are called in the model. If you've done it without, you'll just have the left-hand column, right? It's not a big problem. You don't have to do it. So for age, then we have this marginal impact. For income, we have a marginal impact, and for gender, we have a marginal impact, and we can all interpret those accordingly. So how do we do that? The output shows that marginal effects on the dependent variable are very small changes in the predictor variable. Okay? The output shows the marginal effects on the dependent variable of very small changes in the predictor variable. These changes are at percentage points, and increasing age by 1 year reduces the propensity to smoke, the probability of smoking by 1.19 percentage points on average. Okay? Similarly, for income, a unit increase in income reduces the propensity to smoke by 9.42 percentage points. And similarly, because gender equals 1 for males, then males are 7 percentage points more likely than females to smoke. But that's a bit odd because you can't really change genderness. So it's a bit of a false marginal effect. Okay?
Sorry, can you repeat the interpretation for the male?
For male, it's saying that because it's positive, then males are more likely to smoke. You can't change maleness by whatever DX stands for. DX stands for a minimal change, right? A marginal change. But you can't change maleness or femaleness. So it's a false. You're trying to impute a process that's not relevant for this variable. You can ask yourself, what's the likely effect for a small change in income? But you can't really say that for a small change in gender. Okay? You can't measure that change. But this is an estimation process, and it does the process, but whether or not it's interpretable, reasonably interpretable, is another matter. So you have a question?
So am I right in saying this is different from a normal regression because we only look at like the marginal, the extreme small changes in like income and stuff like that?
No, you can look at unit changes, but it depends on what you're modeling really. These are probabilities, and the outcomes are always going to be in things that are less than 1. Oh, let me hold fire on that for a second. Because there's a linear probability, there's another model that can give you probabilities greater or less than 0, which is wrong, but anyway. But the machinery works, and therefore you can use the machinery to find small changes. Whether or not that's interpretable in sensible terms is a different matter. Certainly not for gender, but you can make a sensible interpretation for income. A small change in income has this effect on the probability of smoking.
And obviously,
and has a small change in age, for example.
Depending where you are on the line, it could, like with age, for example, know that from the previous one, if it's age squared, we know that it might be curved. So wouldn't the marginal effect change depending where you are on the line?
Correct. We'll see that in a bit. All right. So,
Just out of curiosity, where does this one measure it? Does it measure it from 0? Does it measure it?
Well, it's asking. This thing is simply asking for a small change, so it doesn't matter where, in a sense, it's measuring it. It's the average small change across all of the data. In some later on, if we do it, I don't know. We will do it. In fact, I know we won't do it. In some other types of censored models, you would actually get specifically. You can tell it to do a standard deviation change. Okay, so you're actually asking for a certain statistical change, and then measure the effect. But that's beyond what we need to do here.
So, the figures you put, the figures from this data, it says 0.0119362, but when you want to put the data, you said 1.19.
Yeah. So this is interpreted as a percentage change, a percentage. So you divide that by 100 to get the unit equivalent, the percentage equivalent, if you like, not the percentage equivalent, but the amount of percentage change. So it's a bit crazy, but it's percentage points changes. Okay, and percentage points are interpreted as this number divided by 100 to get a percentage.
All the numbers, right?
All these numbers, yes.
So just 2 questions. So one, when you say the unit change in income, does that mean rising of £1? What does that mean?
Well, for this code, yes, it's the derivative. So it's an infinitesimally small amount, not a pound necessarily. You can't measure, yes, but as I said before, in some cases you can tell it to make this a particular measure, for example, a standard deviation.
Okay, I
But
see.
you need to know that, how to code that, and we're not going to do that in this course.
So saying the unit change is good enough.
It's good enough, yes, because this is the derivative. It's really infinitesimally small.
Yeah. So with gender as well, I know we can't measure a marginal change in whether someone's male or not, but could we not? Is it wrong to say that you can interpret that to mean being male makes you, like on average, 0.071 percentage points more likely to smoke? Is that incorrect interpretation?
Because gender is not a variable that you can measure changes in that way, then it's a meaningless. It's really not reasonable to have that type of change.
So we're just supposed to say we can't really draw an interpretation from the results we've seen.
You can, but it doesn't make sense. The interpretation is still the same, that males are 7 percentage points more likely for a small change in maleness. But it doesn't, the interpretation just isn't sensible.
Yeah.
It's still the correct interpretation, but it's not sensible. All right, so let's go back to what else. Why are marginal effects easier to interpret than the results in C? Because the results in C is of an overall effect. So what am I? Can't see. Okay. Similarly, unit increase in income, it reduces the propensity to smoke by 9.42 percentage points. Okay. Using the results from C, predict the probability of smoking for a 30-year-old female earning £300 a week. Again, we should know this code. This is a margins code, and okay. Using the results, sorry. The code for this is here. I'm going to show you my my code, and I'll just talk you through this. Can everybody see my code? What I'm asking is Logit to provide the same regression and then this is how you would do it. Line 53 is how you would write it out if you were doing it manually. You would take the coefficients and you'd put in the estimated coefficients times, for example, here we're looking at somebody who's 30 years of age. So we'll multiply 30 by the coefficient on age. We also multiply 30 squared by the coefficient on age squared. We multiply income by 0.300 and gender by 0 because we're asked about a female, and that would give us the logit. And if you look, what I've done is I've exponentiated. I've called that y hat logit because it's a predicted logit, and then I've exponentiated the predicted logit and divided that by 1 over the exponentiated predicted logit. Okay, if you remember the theory, that the predicted y is based on the exponentiated logit model divided by 1 plus the exponentiated logit model, right? Do you remember that from the theory class? And so that's what I've done. So if I was doing it manually, this is what I've done. I would generate the regression, the logit regression, and then I'll generate the logit, and the logit is going to be the coefficients on the intercept plus the coefficient on age times 30, the coefficient on age squared times 30 squared, the coefficient on income times 0.300, and the coefficient on gender times 0. Once I've created that logit, I need to exponentiate it and divide it by 1 plus the exponentiated number to actually get the predicted probability of smoking for someone with those characteristics. Okay, so I'm just going to run this code and you'll see what it looks like. Don't worry if you don't understand it, because the factor notation is coming up. You could use the factor notation, and here it is. The factor notation is much simpler. You run the model, and I'm saying quietly beforehand, so I don't want the output from the model, but I'm running the model, and then I'm typing margins, comma, at, and then all the details I've been given. Age is 30, income is 0.300, and gender is 0. Much simpler than the code up here. And both should give you the same outcomes. So let me run that code too, and just have a look in Stata. Okay, so here is my longhand. Okay, my longhand thing says the predicted probability of smoking for someone with these characteristics is 0.95130. You can't see the point here because it's at the other end of the line. There it is. Okay, let me just open this, make this a bit bigger, and then you'll see that 0.95130. And if you do it using the logit factor notation, okay, the factor notation I talked about earlier, it will give exactly the same prediction. Okay? Are we all good? Somebody got any questions? And of course, in your computer tests, you would be expected to use the factor notation. All right? So we can predict that someone with these characteristics have 0.95.
Sorry, so I ran the code that
Is in the question?
yeah, on the do file.
Yes.
Okay, sorry.
Do you want to come and have a look, or?
No, I think it's just a way.
Oh, okay, it's a typo. You guys are all okay? All right. Yeah, the wages should be expressed as points, really. 300, because it's measured in thousands. That's why you do that. Okay. So, anybody got any other questions?
So, sorry, just to clarify.
Yeah, go on.
So what we've just done means that we can say that's mean the likelihood of a 30-year-old female who earns £300 a week is approximately 95.13% likely to smoke.
From our estimation, yeah, our model is predicting that someone with these characteristics, that's the probability of they're smoking. So looking at it this way, if you were to pull someone at random from a crowd and they are 30 years of age, they have an income of £300, and they are female, this is the probability they are smokers. Yeah. Okay. So the next thing we need to do then is, using the results from our first model, find the age at which the probability of smoking is maximized. That comes back to your question earlier. Yes. How do we find that? There are a number of ways to do it. Okay, at least 2 ways to do it. And I'll go through the manual way, and then I'll go through the using factor notation. So here is my code for doing it. So again, I'm quietly running the regression, and then what I'm doing is I'm taking the minus age divided by 2 times minus, I'm taking the coefficient on age minus the coefficient on age and dividing it by 2 times the coefficient on age squared, okay? And that comes from a differentiation of your model. Let me just put that on the board and show you what I'm talking about. Well, actually, I've got it here in my do file. So what you're doing is you're taking your, I'm showing it here. I take my model and I differentiate it with respect to age, and everything else that's not related to age drops out. This is straightforward differentiation, right? And you get beta 1 because that's the code on age, and then you get 2 times beta 2 on age squared, and then you solve for age. Okay, so you make this equal to 0, the first order condition, make it equal to 0, and solve for the value of age, which I'm calling here this age squared on my line 85, and that's minus the coefficient that you're trying to find the turning point for, divided by 2 times the coefficient of the squared variable. Okay, and that will always give you the turning point. And if you look at my stator, that is 27 years, approximately. 27 years and change. What's a fourth of a year? I guess just under 6 months, maybe 5 months, something like that. 0.4 of a year, whatever that is. About 27 and a half, just under 27 and a half years. All right? Is everybody okay with that? And in the factor notation, it's even easier. There's a second method called NLCOM, which is no longer really used. Let me just talk you through NLCOM. So again, we're running the Logit with factor notation, and I'm using NLCOM, which means nonlinear combination. I'm creating a variable called age turning point, and I'm making that equal to minus age divided by 2 times the coefficient on age squared. All right? And when you do that, you get you get 27.38 again. All right? Is everybody okay with that? And then when you use the factor notation one, here it is. You have to decide. No, sorry, forget that. Those are the 2 ways that we need to think about. So that is the details of how to show age, the turning point in age. You just need to differentiate the function, set it equal to 0, and solve for age. Okay, standard mathematics, really not very. That's the deepest amount of mathematics you'll need to do for this course. I mean, it's not very difficult. If you don't know how to differentiate a function, then send me an email and we can have a session to go through it. But it's really not terribly difficult. Okay, any questions so far? Do you have any questions? Anything in the chat? No? Okay, let's keep going then. So now we need to use the following commands to graph the thing. And so type the following commands: margins at, all right. This is asking for you to draw the plot for somebody between age 0 to 60. That's not all the ages in the data set. Okay? But that's what you're asked to do, so just do that. At which age should the government target if it wishes to reduce smoking. Okay, let's run the code. Let's run that code. And you should all have this. And this is the predictions based on the data that you have for values of ages from 0 to 60. We did one, didn't we? One person, female, with income of 300, an age of whatever it was, 30. This is for the same person for different ages. Okay? And this is specific to that person, of course. It's not for the whole data set. Be careful there, all right? Because this relates only to one person. And what is it telling us? Two things to notice here we should talk about, really, is that our predictions are less sound as we move away from the age of that particular person. Can you see that? We know the data for the person is 30 years of age. That's their characteristics. And as we move further away, the prediction becomes less accurate. Okay? So if you were the government, what would you do? What would you say this graph is telling you? Let's assume everybody in the data set has very similar graphs. What would you do? What would you say? The question asks, what does the question ask? It asks, at which age group should the government target if it wishes to reduce smoking behavior? Come on.
So would be 27 again, because that's where there's most smokers.
Well, it seems to me that our model sort of fairly well accurately predicts with this data between the ages of 20 to maybe 40, and less accurately predicts beyond those ages. So given the data that I have, my gut tells me, my instincts tell me that for those ages, they are predicted to be the most likely smokers. And so if I wanted to target reducing smoking, those are the age groups I would target.
So according to our graph, does that say that 100%, or there's like nearly 100% of people according to that?
No, that's not 100% of people.
No, between that are female, that have the income of 300, smoke, according to that graph.
No. This is this thing here is telling us that based on this data, our sample, that for people with this characteristics, that is years of age and income of 300, this is their predicted probability of smoking. We're not saying that 90% of them are smokers. We are saying that given our model predicts that a large proportion of these people, the people with these characteristics, are likely or have a propensity to smoke. And so I would, as the government, want to target this group. Okay? This is one of the issues with limited event variable models, really. You know, you can only talk about the range of the outcome variable, and in this case, goes from 0 to 1. So it seems then that the age 20 to 40 is the age you might want to target. Everybody okay with that? Was there any questions? Did I hear a ping? Aaron says between 20 and 35. Yeah, that will do, Aaron. That would be working. So, how do the results differ? How do the results that you obtain differ if you use the Probit model instead of the Logit model? Okay, in the theory, we didn't get so far down this, and as I said then, on Monday we'll be revisiting the end of the lecture notes from last time, but we didn't talk too much of the Probit. Here is our chance to have a look at it in a bit more detail. So what do? Well, we just run the Probit model. Okay, and here's the code for it. Oh, come back. Oh. So what have I done? Oops. What did I do? So I created a Probit model. This EST store is simply telling Stata to store the model details for me. Don't worry about it. It's a code that I use for, and you'll see in a second, there's a table that you can produce. It's really only for teaching, or well, for those of you who want to publish things in nice formats, this code allows you to produce nice tables, and if you need to, we'll talk about it when you come to do your dissertations in the summer. Okay, if you want nice tables, we'll talk about it then. In fact, I run a session in the summer on graphs and outputs. So you know the dissertation skills workshops that you have to go to, one of those on graphs and presentation of your results and stuff. Anyway, this code will allow me to produce a nice table. But here is the Probit model anyway. The Probit and everything that you had before, and this time I've asked that I don't have the iteration output. I mean, I mentioned that earlier. If you didn't want the iteration output at the start of the regression table, you can ask for no log. Okay, and there it is. And what you want to do then is to compare those coefficients to the to a table of the Logit. And here's that nice table I was telling you about. I'll produce the table that says here's the Logit predicted probabilities, and here is the Probit predicted probabilities. And what can you say? What can you say? Say what you see is what you should do. Okay. First thing to notice. First thing to notice is that the probabilities in the Probit are all smaller than the probabilities in the Logit. Okay? As is the standard errors. So they all produce smaller probabilities than do Probit. This is a problem, or could be a problem, because the choice between Probit and Logit is a choice between the link function that we talked about in the theory, right? We need a function that changes our observations to a system where they can be converted into 0 and 1. Sorry, they can be converted into probabilities ranging from 0 to 1. And that requires a link function. And the link function of the Logit is the standard normal tables, standard normal cumulative density function. And the link function of the Logit is the logistic function. The logistic function is a exponentiated model divided by 1 plus the exponentiated model predictions. Whereas the Logit also, if you know, sorry, the Probit, if you understand the cumulative density function for the standard normal distribution, then it ranges from 0 to 1. and so it gives you the same space to map into as does the logit, but the probabilities are slightly smaller. So when we were talking about interpretation before, it becomes more tricky, doesn't it, to say that the same amount of probabilities generated by a change in age in the logit model as the probit model. It's clearly not the case. But the standard errors are also smaller, so the significance should be the same. But it's just, and the signs should be the same, okay? The signs should be the same, and that's good. If the signs are different, then you have a problem. Something's gone wrong somewhere. So what do we say? The coefficients are all smaller in the probit model, but the standard errors are smaller as well. The asymptotic t statistics are roughly the same. We've only got the standard errors there. I haven't asked for the t statistics, but we could look at the t statistics in for example, on age in the probit model is 6.57, and in the logit model it's 6.3. So it's fairly similar, isn't it? So in logit, the t is, sorry, the equivalent of t, it's a z, but we talked about why that was in the theory class. In the logit, it's a 6.3, and in the probit, it's 6.57. On age squared, it's minus 8.35, and in the logistic, it's minus 7.8. For income, it's minus 4.04 in the logit, and for the probit, it's minus 4.16. So they're very similar t statistics, or t equivalent statistics, asymptotic t statistics. And we talked about why the probability for the p-value is a z value, right? So, and you can see they're all statistically significant. So you can say that they are smaller in the probit than the logit by approximately whatever it is, 1.8, and that's usually equal to pi divided by root of 3, or something similar like to that. Okay, but the predicted probabilities have the same ranking. For example, they're not the same number, as you can see in this table. They're not the same number, but their ranking will be the same. Okay, so the effect of age with respect to the others will be exactly the same in the probit and in the logit model. Okay, the predicted probabilities and the marginal effects will also be the same. So we could check that. We could check the marginal effects. Let me go back to my code. I've just shown you what the proportional difference is between the probit and the logit for the age beta, and that is, it suggests that probit is about 55% of the logit value for age. So this number here is about half of that number there, but it's not the same for each one. So it will be different for each individual. Okay. If we the predicted probabilities, the marginal effects should be the same, but for rounding difference. So we could check that. Here is the code to do that. So here's the code from probit. So we run the probit model, and then we run the margins command to the same individual who is 30 years of age, income of 300, and gender equals 0, and then calculate the turning point for that person, That's their marginal effects, right? We've done that already for Logit. And what do we get? We get 27.12. Whereas for Logit, what did we get earlier? 27.38. So the marginal effects are the same, regardless of whether you use the Probit or the Logit. And remember, the marginal effects are easier to interpret. Yes? Because when you're using the estimation process, all you're getting is a predicted probability that you'd have to put through a mincer to get the actual value out, right? Whereas the marginal effect is easier to interpret. So here's the marginal effect from the Logit model, 27.38, and here's the marginal effect for the same person using the Probit model, 27.13. Okay?
So I thought that was just the age at which the probability smoke was maximised.
For this person, yes. So that is a marginal effect, isn't it? To find a maximum, you take the first derivative, yes? So I'm just using the same details for the same person with using the Probit model as with the Logit model and comparing the two outcomes, and they're approximately the same. That's all we're saying. Okay, let's get back to any questions. Any questions so far? Are we all good? Everybody happy? Okay, so 3 more bits and we're done. Add an interaction term in the model. Now, we haven't covered this in the lecture notes, and I'm going to cover it. I'm going to talk about it next Monday. So this is an advance of what I'm going to say for the theory that covers this. This is the application. So when we want an interaction term, what we have to do is to create that term, and it's effectively multiplying the variables together, and that's what this command is doing. It's asking. Now it has, if you notice, it has 2 hashes. One is asking for age and age squared, and one is asking for income, and income interacted with the male variable and female. Okay, but as of course, this is a general form for any indicator variable. I means an indicator variable. C means a continuous variable. Okay, be careful when you do this. You need to tell Stata that C, your variable is either continuous or it's an indicator variable, it's a factor variable, okay? And to do that, you need to put I in front of it. So that's the code, and then you need to interpret the coefficients with respect to this. And we're going back to the Logit, okay? We're modeling in Logit this time. So get to my before I do that, I didn't show you a table. Here's a table of the marginal effects for both models. It's not been asked of you by Peter. It's not in the question sheet, but I've done it anyway. And this is what it looks like here. This is my table output. What I've done here is I've simply asked Stata to run the regression for Logit and for Probit, which you've already seen in the first table, right? These are the same table, and then produce the marginal effects. So Logit's marginal effect and Probit's marginal effect, and you can see that they're approximately the same. Okay, so the marginal effect for income between in the Logit model is minus 0.09 percentage points, and in the Probit model it's 0.9, well, it's 9.7 percentage points, right? Similarly for gender, 7 percentage point change, and 7.1, 7.10, 7.14. So this is just showing you the marginal effects in the two models produce the same numbers, okay? But you didn't need to do that. Peter didn't ask you to do that. And the code, I use this here. So run the regression in Logit and produce the margins for Logit and save them. Do the same thing for probit, save the margins command. Sorry, the margins output. Store means save the output, right? Store the margins command for there directly after the logit. Store the margins command directly after the probit, and then produce an output table with first regression, second regression, and the two further regressions are these two here, producing standard errors and the titles and so on. That's pretty much. Now you don't have to go to the workshop on Monday. Well, there's more to it than that. Sorry, on Monday in the summer, there's more to it than that. So add the interaction term and interpret the value. So here it is again. First of all, I create an interaction. In my case, gender times income. In your case, might be male times income, right? Run the logit model, and then if you wanted to use the factor notation, as you saw in the question, you would have to use male here if you haven't changed to gender. This is why I told you at the beginning, if you wanted to follow my code exactly, you needed to change to gender, but there it is. And then you're asked to plot the difference. Well, I'll do the plot as well, and then we can talk about both. I'll show you the code for the plotting a bit in a minute. So here is the output. What can we say? We're asked to run the code, or add an interaction term and then interpret it. So what is the interpretation of the interaction code? What does it tell us? The interaction between income and gender is negative. Okay? It suggests that males, it suggests that well, first of all, let's have a look at this income variable here. This is the income variable we had before, and what do we notice about it when we add the interaction term? It's become insignificant. Okay? So income is not significant. For what? If this is this coefficient here is the coefficient that tells us the income effect for gender, who does it relate to? Males. Good. So this is the income effect on gender, and gender equals 1 means males, right? So as income increases, you would expect the probability of smoking, the predicted probability of smoking, to fall. Yes? With income rising. Not so for females, because the alternative is not significant. Are we good with that? So the coefficient of male with income is negative and significant. Therefore, and notice that the income is now essentially 0, and that is telling us that for females, income has no effect. While for males, what does it say about males? It's effectively saying if you increase income, what is the predicted probability going to be? It's going to fall, which makes smoking, or whatever they smoke, an inferior good. Yes? This is the economics part. And in the questions, they're going to say, use economic interpretation, right? This is what they mean. If income rises and you buy more, it's a normal good. If income rises and you buy less, it's an inferior good. That's the economic interpretation. Means it's an inferior good, whatever it relates to, in this case, smoking. Yes? For males. For females, not so much. You have not any, you can't say that. You don't know because it's not significant. So you don't know the female impact for smoking, but you do know the male impact, right? And then we could sort of graph that. We could graph that, and let me show you what the plot looks like. Why did you not work? Let me just try it again. There we are. And you can see clearly, I hope, that for when gender is 0, income has no change effect, pretty much. Yes? But for gender equals 1, males, has a negative effect. Also, you should note that when income is 0, males are still more likely to be smokers than predicted to be smokers than are female. Yeah?
So sorry, just clarifying. So in the regression, when it says 1 dot male, that's just likelihoods, the increased likelihood for males to smoke before we interact.
What 1 dot male? No, that's not 1. That's I.
Oh, is that sorry.
I dot male.
Yeah.
It's an indicator. It's telling Stata that it's an indicator variable. It's a factor variable.
Yeah.
So it has limited ranges. Whereas C dot whatever variable would be telling Stata that it's a continuous variable. So for when you know the variable is continuous, like income, for example, it's a continuous number, age, continuous number, then you put C age or C income in the regression command. Okay? That answer you? What was your clarification for?
Yeah, I'm so sorry. Just when we were looking at regression, I was just wondering what does I dot male tell us? Is it like how can we separate the coefficient from? Oh, sorry, I dot gender.
I dot gender.
Yeah.
Okay, so this is the effect of gender on the probability of Y, which is the probability of smoking. So gender has a positive effect on smoking. So that's male.
Yeah.
Being male, you're more likely to be a smoker than none.
Yeah, sorry, I was just asking, is that is just the effects before we interact with income, right?
No, this is the income interaction with gender. That's what this is telling you here. Now this is what in the note, because you put it this way, you've got double hash here. You're telling it, give me the age effect and the age squared effect. Give me the income effect and the income with gender effect. The 2 hashes. You could do it 1 hash if you just only wanted the 1. Okay? That help?
I think okay.
Try it with your machine with just 1 hash here, and you'll see the difference. Okay? You won't get the income separately or the gender separately. You'll get the interaction. Anyway, have a look and see. What are we looking at next? So it asks us to add the class variable to the logic command, and then use the likelihood ratio test to test the significance of the occupational classes in determining smoking behavior. Why do you think occupational class is relevant in the smoking decision? Which class smokes and which class smokes? Sorry, which class smokes most and which class smokes less? Everybody get that online? Everybody okay online? So that's what we're going to do next. So for me, I've just defined, there are labels missing from the class variable, and I'm just creating some labels here, so don't worry about this in your code. I'm just putting some labels to tell me that class 1 is professional, class 2 is intermediate, class 3 is manual, and class 4 is unemployed, because they're there are no labels in the data set. And then I'm running the logit with the interaction between income and gender, and then adding class to that, and adding also age and age squared to my model. Okay. And there it is. Here is the model. What can it tell us? Let's start with the interaction terms. It tells us that this is the predicted probabilities for these categories of employees for their propensity to smoke. And it's all positive. Compared to what? Compared to the excluded class, right? Remember that when you interpret dummy coefficients as indicator variables, the right-hand side variables, you're always interpreting it with respect to the excluded category. And so intermediates are more likely to smoke are predicted to be more likely smokers than are professionals. Manuals more than intermediates, and unemployed the most likely to smoke. So you can, if you like, rank it from highest to lowest predicted probability of smokers, or propensity to smoke. And then you're asked to carry out a likelihood ratio test. What's the likelihood ratio test? If you remember from the lecture, it is twice the difference between the full model and the restricted model. What's the restrictions? The restrictions are the likelihood from the model without the interactions. So it's this one here. This is the likelihood. It doesn't have the class variable in it. So in this model, it's restricted because we're restricting the coefficients on that variable to be 0. Yes? And if pretend it's in this model, but all the coefficients are 0, that's the restricted model. Yes? The unrestricted model is this model with them all in, where their coefficients are not 0. So it's clear which is the unrestricted log likelihood, yes? And what is the restricted log likelihood, okay? Are we good with that? And as you know, the likelihood ratio is 2 times the unrestricted likelihood away from the restricted likelihood. So in this case, I don't have an overhead to write on, but that would be 2 times minus 1658853 minus 197.45. And when you work that calculation through, it comes to 63.137. Okay? Let me see if I can show you that in the answer, because I think you should see it. Let me change what I'm looking at. Just bear with me a second. I've got to stop sharing the screen and share instead my camera, okay? Just for a second. Oh, maybe not. Damn it. Why can't you show it me? Can't access the camera. Why can't you access the camera? It's there. Can you use log technology? Yeah. Okay, I'm sorry, I can't show you the solution. Okay, I do apologize. Oh, hang on. No, I can't even share that camera. Boo hiss, boo hiss. Okay, going back to where we were then, I've got to choose one. No, why don't we do that? I'm stuck in a forever loop now. Okay, let me try and come out of this nightmare. Okay, I'll do that. Now I can stop doing that. Oh, hang on. Wait a second. No, I don't want to stop that. I've just realised I have a camera that I could share. Foolish me. No, it's not that one. It's that one. No, it's not that one. I just saw it. Come on. No way. USB capture HDMI. Yes, there we are. Okay, hey. Look, can you see this? Oh no, it's upside down. Is that the right way up?
I think they start sharing first.
Aha, good, yes. Share the camera. Good, it's upside down anyway. Look, this is what I'm talking about here. First of all, can everybody see the screen? Tell me you can see the screen. Talk to me, because I can't change the screen to see your, yes, well done. Thank you very much, Jeremiah. So what I'm saying is you take the difference in the logistic for the unrestricted minus the log likelihood for the restricted model, which are these two numbers here. Okay, so it's minus 165 minus 179. And when you do that, you get 6.63.13. That's a big number, okay? And you need to compare that to the chi-squared, the test statistic, the likelihood ratio to test statistic has a chi-squared distribution with 3 degrees of freedom, okay? So we're saying that these dummies have no effect, and those are 3 restrictions, and the test statistic, the critical value is 7.82. All right, 7.82 will give you the critical value, and so you have a way of deciding whether or not the to reject the restrictions or not. So here it is in Stata.
So can you say again why it was you multiply by 2?
Because that's the test statistic. That's how it's done. So many years ago, somebody sat down and worked out.
So it's always going to be 2.
It's always going to be 2. Yes. It's no. When you design this test statistic, it is what it is, right? It's a formula, and that formula is what it is. Once you've got that formula, for whatever reason, you'd have to look at statistical theory for that. For whatever reason it is, you then stick samples into it. You do a simulation and you look at the distribution of it and compare it to a known distribution. That's effectively what we're doing. For some reason, it's telling me it hasn't found, because I haven't probably done it. Okay, so I'm just rerunning my code because I didn't do it. I was talking to you. Let me see it work now. Okay, so what did I do? I calculated the restricted model, which does not have the class variables, and then the unrestricted model first, and I captured the log likelihood. If you remember back in session 3, I gave you a way of getting the output that Stata saves. Remember E returns list? Yes, you remember that code, E returns list? If you type it after a regression output, for example, if you do this logit regression now, either restricted or the unrestricted one, type E returns list, and you will see that ELL is the estimated log likelihood number, okay? And I've simply generated a name for that. And then if you look at my code, let me just go through my code, it'll be easier. Here we go. What did I do? For the unrestricted model, I had the class variable in, and then I typed E returns list to find out what the likelihood.
I can't see your screen.
Oh, okay. Thank you for that. Let me just go back and share my screen. Why aren't you? Just bear with me a second. I can get to the chat, and I can get to the content, and I'll share my application screen, the entire screen, and we should be back in business. Okay, thank you. So what I did was, here's my code. I first ran the unrestricted model, which is here, quietly run the logit with the class dummy in, and then using eReturnList, I found out that ELL is the log likelihood, and I've captured that, given it a name. I've done it the same thing for the restricted model, and then I've calculated the statistic, and then I compare it to the chi-squared. And I don't know if I've told you about this, but Stata has inbuilt all the tables you need. So if you wanted the t-table, you'd ask for the inverted t. Here you have the inverted chi-squared tail, and with 3 degrees of freedom and 0.05 as the alpha value. Okay? And when you do that, you get the critical value from that code will give you 7.81, and you know from the calculation that the likelihood ratio test statistic is 63.37. Therefore, we have evidence to reject the null. Remember, the null is the restrictions are valid. Okay? Everybody happy with that? How do we do it? You want the code? I'll just put the code up again so you can see it. There's the whole thing. Go on.
I was just saying, what does E mean again?
E is estimates. So you're asking Stata to give me a list of all the estimates that it's returned in your regression call. If you just type your logit model in now, and then type E returns list, it will give you a whole heap of things that Stata collects when it does a regression call. Okay? I've just captured one. Everybody okay with that? And then what I've done is I've asked Stata to tell me from its tables, it keeps tables, what is for the inverted chi-squared, the tail distribution, what's in the tail with 3 degrees of freedom, 3 restrictions, and alpha of 0.05.
And sorry, so I thought the only restriction was class. Why do we have 3 restrictions?
Because these are the restrictions on the dummy variables. There are 4. Yeah.
That makes sense.
There are 4 dummies, and the first dummy, the excluded one, is 0 anyway, right? Are we okay with that? So there are 4 restrictions generally. 4 restrictions that -1 basically. Don't worry too much about that. You can look at we didn't cover this in the theory this week because we didn't have time, but I will cover it next week briefly. Okay? Because the likelihood ratio test will come again further down the line. All right. Okay, so that's whoops. I have to stop sharing, reshare. No, I can do that. I can do that. Yes, here we are. So we've now added class. Why do you think occupational class is relevant to the smoking decision? What classes smokes the most and which class? Okay, we know which one smokes the most and which one smokes the least. We've done that. Okay, we've done this regression. We can see that unemployed smokes the most and professional smokes the least. Why might that be?
So this is just sort of we can give like just intuition.
Economic interpretations. And you guys don't do economics, do you? Come on, say what you think. Give it a guess. The worst you can do is get no marks for that part. You can still do the regression, right?
I don't know, maybe the unemployed might be associated with high levels in jobs, you might have hope because it's smoke.
Good, good. So you have to make some assumptions.
Yes.
Okay, your assumption might be that people with low income suffer stress more than people with high income. If that's the case, higher income people are much less likely to smoke than low income people. The second assumption is that professionals earn more than the unemployed, which is a reasonable assumption. Somebody just asked me a question. In the chat, where's the chat? Oh, somebody's just left the session. Oh, that's a shame. Oh no, here we are. So somebody has, due to the variation in income, yes, that would imply what? You have to make some assumptions and state them, right? The assumption made here is that people unemployed will earn less than professionals. And there's another one too. A second reason might be, we know, do you have something in mind? We know that people who earn more money are generally healthier. They have healthier lifestyles, yes? And that might be a lifestyle choice for the people with money than compared to the people without money. So that's an observational issue. Inferior good. Yes, we've noted it is an inferior good for people on higher incomes, haven't we? Well done, Krishna. So use these sorts of arguments to make the case, all right? What does the answer itself say? It says, no, it talks about the Wold test as an alternative test. Yeah, in the answer, when you get the answer, it'll talk about there's an alternative test to the likelihood ratio test, but I'm not going to go through that. I'll leave you to go through that because it's a Wold test. It's not a likelihood ratio test. So it's not valid in small samples. Read about that. So I'm running out of time, so I'm going to finish off the final question. Which class smokes the most? Which can we've done that. Why? Explain why income appears to have a negative effect on the probability of smoking in the model in C, but a positive effect for the model in J. Good question. Good question. Why does income appear to have a negative effect on the probability of smoking in model C, saying it's a inferior good, and a positive effect on smoking in model J? I wonder if I have KaiDemo. I'll just check. I don't think I've got KaiDemo loaded. No, KaiDemo isn't loaded. Don't worry about that. It's just in my code. I'll talk to you about that if you come to the dissertation workshops for in the summer. Okay, so explain why income appears to have a positive effect in one model and a negative effect in the other. So let's have a look at these models. I'm just rerunning the models there, and we can graph these effects there. Okay, let me just go back to this. Here is the two models. Okay. Model 1 is the one without the class indicator, right? That is the restricted model. And in the restricted model, income is negative effects, yes? But in the unrestricted model, it's a positive effect. Okay? Forget about all of this here. I've just included interactions and that we don't need. But what we're talking about here is the first model has an income effect that's negative and significant. Okay? And the second model has an income effect that's positive, although it's not significant at standard levels of analysis. But the question is, why has the sign changed? Anybody got any?
Because we now take into account class, so that may be a bigger influence. That may be the main reason why it has the effect. So that would be good parts.
If you got answers, you can probably hear me from so far. If you've got answers, put some answers for the people online. If you have answers, put some answers in the chat, and I'll refer to those. Somebody just said that
It's because class was the main influence. So before, income was seen as the reason why, but income was only, I'm not sure what the terminology is.
yeah, I'm going to give you that in a second. You're struggling gainfully, having the right answer in your head, but not terribly well. That's good. Yeah. The income effect operates through the class variable. Okay? So the effect of income is not strong on its own. It operates through class. Sometimes you'll find the income operates through gender, as in this case, because gender, when females are looked at, income doesn't affect their predicted propensity to smoke. Yes? And so what we say is that when we account for class or social class, then the income effect is strongly through that variable rather than the other variable. And so even though the second one is less significant, is not significant, the sign is probably correct. So another way of looking at this, and this is the final thing I'm going to do before I finish. When you draw this thing, and I need a pencil here. I apologize for the noise that's going on in the background. Okay, I'm going to change the view from that screen, which is to this screen. Okay. Can everybody see the? I'm just going to ask people, can they see my screen? I have to stop showing the entire screen and share instead. Which camera? I think it's that one. No, not that one. Let me just find the camera that I was looking at before. Is it that one? Come on. Oh, hang on. No. Oh, hang on. How did I find that other camera before? Where was it? Was it that one? Focus. It's not that one because it's plugged in here. Maybe I can do that one. Will it show you that one? Oh, now. Oh, here we go. I'll just. Okay. This is. I'll do it this way. It takes a while. There we go. Okay. Can we see this now? Can you see it now? I'll share it now. It should be there. Tell me you can see my screen now, everyone. Can they see it? Can you see it online? And what we're saying here is when you've got, first of all, can you see it? Zengwo, was that a new yes? Or was it an old? It is, it's the current time. You can see my screen. Excellent, thanks, Mary. So what it means then is this propensity to smoke for the income variable operates through social classes, okay? And before you saw the negative effect, and that was because the density in the low social class of observations is likely to be at the low end of the income scale. Yes? Whereas the density in the high end of the income scale is likely to be with the people of the higher social class. Yes? And the simple model before, without social class, was simply measuring this effect. And that's why it was negative. Yes? Whereas when you put social effect in, you can see then the income effect through social class is positive. I'm not sure if I've really said that as clearly as I might. So what we're saying, I mean, of course, there are people on low income, low social classes that have high income, and similarly, there are people in the higher social class that has low income. But the mass, the majority of the observations in these classes are likely to be for the low social class in the low income range, and for the high social class, for the high social class in the higher income range. And that's why when you don't include them, social class, in the first model, we got a negative effect. Okay? I have no idea how difficult that might be to say in an exam, but that's what you want to try and show. Okay, does everybody got any questions before I wrap up? Are we all good? So next Monday, I don't know how your timetable's looking, but the lecture is again next Monday morning. I don't know if you people online had today's lectures on your timetable. If you still haven't got your timetable sorted out for these sessions, please let me know. They will be happening every week at this point in this room at this time, and the lecture similarly on Mondays. And if you don't have any further questions, I shall stop the recording.
Can you please check? I'm trying to open the document for notes with 9. It's not opening.
Okay, bear with me a second. I'm going to stop the recording.